Beneath our feet lies a world we rarely imagine, layers of rock, minerals, heat, and mystery stretching kilometers into the planet's heart. For centuries, humans have wondered what lies deep beneath the crust, beyond the reach of caves, mines, and natural vents. The idea of venturing deep into the earth, to the place where our planet's history is recorded in stone, has fascinated scientists, adventurers, and dreamers alike. This fascination became reality with the creation of the Kola Super Deep Borehole, an audacious Soviet-era project designed to pierce the Earth's crust further than any human endeavor before. Drilling through kilometers of rock, scientists sought not only to measure temperature, pressure, and geology, but also to peer back into the ancient past of our planet. The deepest hole ever drilled would become a window into a world largely unknown, a slow, deliberate descent into silence, heat, and time itself. As we journey into the story of the Kola borehole, we explore not just the scientific findings, but the human curiosity and quiet persistence that made it possible. In this exploration, the Earth speaks in layers of stone, fluid, and heat, whispering secrets held for billions of years. This calm investigation reveals a world both alien and familiar, a reminder of the delicate complexity of the planet we call home. Section 1. The Kola Super Deep Borehole, a journey into the crust. The Kola Super Deep Borehole, located on the Kola Peninsula in Russia, is a testament to human curiosity and persistence. Beginning in 1970, the project aimed to explore the Earth's continental crust in unprecedented detail. Engineers and scientists faced a challenge unlike any before, drilling not just but tens of thousands of meters into solid rock, into a world where temperatures and pressures grow extreme with depth. By 1989, the borehole reached a depth of 12,262 meters, over 12 kilometers, a feat that remains unmatched in human history. Drilling at such depths is far from straightforward. The Earth's crust is not uniform. It consists of alternating layers of granite, metamorphic rocks, and sedimentary deposits, each with unique hardness and composition. Conventional drilling techniques could not simply be scaled up. They required innovation, patience, and careful observation. The drill had to withstand immense friction, vibrations, and heat, while operators had to navigate challenges invisible to the naked eye. Each meter achieved was a small triumph, a quiet victory in a project that required years of methodical effort. The deeper the drill penetrated, the more surprising the results became. Scientists initially expected the crust to become uniform at depth, but instead, they discovered a complex, fractured structure with rock layers that had formed hundreds of millions of years ago in ways difficult to interpret. The drill passed through metamorphic rocks shaped by ancient tectonic collisions, revealing that the Earth's crust is far from static. It is a living, shifting record of a planet constantly in motion. One of the most intriguing findings was the temperature gradient. Scientists anticipated that temperature would increase steadily with depth, but measurements showed that the heat rose faster than expected. At the borehole's bottom, temperatures reached around 180 degrees Celsius, far higher than the predicted 100 degrees Celsius for that depth. This unexpected heat slowed drilling and suggested that the thermal structure of the crust is far more dynamic than previously understood. Even in its silence, the Earth hinted at hidden energy and processes that challenge our assumptions. The Kola borehole also revealed surprises about fluid movement deep underground. Water was found in cracks and fissures within rocks thought to be impermeable, showing that the crust is not a dry, static mass, but a porous, interconnected system. These fluids likely migrate from surface and subsurface layers, influenced by pressure and temperature. The discovery opened questions about the role of deep water in geologic processes and even the possibility of deep microbial life, tiny organisms thriving where light does not reach and conditions seem extreme. Perhaps the most poetic discovery was that of ancient fossils and microscopic life, indicators in rocks thought to be devoid of life. Tiny remnants of past microbial activity suggested that life, in some form, may have penetrated deep into the crust for eons, surviving in heat, pressure, and darkness. These findings reminded scientists that the Earth is not simply a static globe of rock, but a living system, with history recorded in every mineral and fracture. Each layer became a page in the silent story of our planet, a chronicle spanning hundreds of millions of years. The Kola superdeep borehole also taught humanity about the limits of technology and endurance. Drilling slowed as heat increased, equipment failed under pressure, and scientists learned to adapt to conditions that seemed insurmountable. Patience and careful observation were as critical as engineering skill. The borehole, in its silent depth, became a monument to curiosity, a record of persistence against the slow resistance of the Earth itself. By reaching 12 kilometers, the Kola borehole pierced only a fraction of the crust, roughly 1/3 of its total thickness under the peninsula. Yet the information gathered reshaped our understanding of geology. It revealed the intricacy of rock formations, the unexpected distribution of heat, the movement of fluids, and the faint traces of ancient life. It reminded humanity that the Earth, even beneath our feet, remains a vast, mysterious, and richly detailed world, one whose secrets unfold slowly to those willing to listen and observe with patience. As we descend further into the story of the borehole in the coming sections, we will explore what lies beyond the Kola project, the chemical surprises, the implications for understanding the Earth's history, and the questions it raised about life in extreme conditions. The deepest hole ever drilled is more than a scientific achievement. It is a meditation on patience, curiosity, and the quiet, hidden complexity of the world beneath our feet. Section 2. Unexpected discoveries in the deep crust. The Kola superdeep borehole, as humanity's deepest artificial window into the Earth, was not only a technical triumph, but also a source of astonishing and often unexpected discoveries. As the drill penetrated deeper than 12 kilometers into the continental crust, scientists encountered a realm that challenged conventional geological wisdom. Each layer brought surprises, revealing that the Earth is far more complex, dynamic, and alive than anyone had anticipated. The borehole became not just a technical project, but a meditation on the quiet mysteries of our planet's hidden depths. One of the first unexpected findings was the composition and age of the rocks. Geologists expected a relatively uniform progression of rock types, with increasing depth. Stable metamorphic formations, overlain by ancient sedimentary layers. Instead, the crust was a patchwork of intricate interleaved rock sequences, each telling a story of tectonic collisions, volcanic activity, and mineral transformation spanning hundreds of millions of years. Certain layers, thought to be relatively young, revealed themselves to be far older, carrying chemical signatures that hinted at a complex history of continental evolution. Every meter drilled seemed to rewrite a page in the Earth's story, proving that the planet's deep interior is anything but simple. Perhaps the most striking discovery came from the presence of water at extraordinary depths. Conventional geological models had assumed that water exists primarily in near-surface aquifers or within porous rock closer to the crust's upper layers. Yet in fractures and fissures deep in the Kola borehole, scientists found water trapped in rocks thought to be impermeable. These tiny volumes of fluid, squeezed under extreme pressure, suggested that the Earth's crust functions as a vast, interconnected system. Water moves, albeit slowly, along hidden pathways, influencing mineral formation, chemical reactions, and even heat transfer. In essence, the planet beneath us is not dry and inert, but a subtle network of fluids and energy, quietly shaping the evolution of the crust over eons. Even more surprising were the traces of ancient microbial life. Rocks previously considered sterile revealed microscopic features consistent with microbial activity, preserved in mineral structures. Though the borehole was not designed to study biology, these findings hinted at life's remarkable resilience. Microorganisms may have survived in the darkness, high pressure, and elevated temperatures of the deep crust for millions of years, possibly deriving energy from chemical reactions rather than sunlight. This discovery transformed the Kola borehole into a kind of subterranean laboratory for astrobiology, offering clues about the potential for life in extreme environments elsewhere in the solar system. From the icy moons of Jupiter to the subsurface of Mars, chemical analyses revealed unexpected distributions of minerals and elements as well. The deeper rocks contained higher concentrations of certain rare elements than predicted, including radioactive isotopes like potassium-40 and uranium-238. These isotopes contributed to localized heating, explaining the higher-than-expected temperatures measured at the borehole's deepest points. The discovery challenged pre-existing models of the Earth's thermal gradient, emphasizing that heat flow in the crust is neither uniform nor entirely predictable. It is influenced by chemical composition, fractures, and historical geological processes, creating a landscape of energy that shifts quietly over millions of years. The borehole also unveiled unusual seismic and acoustic phenomena. As drilling proceeded, scientists recorded vibrations, sound waves, and microfractures within the rocks that suggested the crust is far more fractured and mobile than previously assumed. The deeper the drill went, the more dynamic the rock layers appeared, subtly responding to both natural stress and the mechanical presence of the drill. These vibrations offered a quiet symphony of the Earth's inner workings, a delicate reminder that even seemingly solid rock is never entirely static, and that the planet's interior is alive with movement, tension, and gradual transformation. Temperature, as mentioned in earlier observations, became one of the most compelling and limiting discoveries. The heat at depth rose far faster than predicted, reaching around 180 degrees Celsius at 12 kilometers. This higher than expected gradient meant that drilling required careful cooling and constant monitoring. The phenomenon also implied that the Earth's crust is not a simple insulator, but a complex thermal system, shaped by the distribution of radioactive elements, fluid pathways, and the history of tectonic stress. Temperature, pressure, and chemical composition are intimately linked, creating an intricate balance that governs rock behavior at depth. One of the quieter but deeply philosophical aspects of the borehole was the sense of time encoded in the rocks. Each layer represented a chapter in the planet's long history: collisions of continents, the rise and fall of mountain ranges, ancient oceans that had long since vanished. Drilling became, in a sense, a journey backward through geological time. Every meter added was a meditation on scale, patience, and the slow evolution of the world beneath us. Humans, with their brief lifespans, glimpsed moments in the life of the Earth that span hundreds of millions of years, offering a humbling perspective on our place in the natural order. The borehole also revealed the limits of human technology. Equipment had to withstand extreme heat, high pressures, and the unpredictable behavior of fractured rocks. Drill bits wore quickly, casing had to be reinforced, and teams had to adapt continuously to unforeseen challenges. Yet the project endured, a testament to persistence, ingenuity, and careful observation. In its depth and complexity, the Kola borehole became more than a hole. It was a dialogue between humans and the planet, a patient negotiation with the Earth's hidden layers. Ultimately, the unexpected discoveries of the Kola super-deep borehole remind us that the Earth is far more than a collection of rocks. It is a living, evolving system, rich with energy, hidden fluids, ancient life, and the memory of countless geological events. The borehole serves as a profound meditation on curiosity and the limits of perception. By venturing into the deep crust, scientists did not simply drill a hole, they opened a window onto a hidden world, revealing both the resilience of life and the intricate beauty of the planet itself. As we move into the next sections, we will explore the implications of these findings, including what the borehole taught us about the origin of continental crust, the deep biosphere, and the future of extreme drilling technology. The journey into the Earth's interior is far from over, and each discovery invites new questions, new reflections, and new awe at the hidden complexity beneath our feet. Section 3. The Deep Biosphere, Life Beneath the Surface. As the Kola Superdeep borehole delved ever deeper into the Earth's crust, one of the most astonishing revelations was not merely geological, but biological. For decades, scientists had assumed that life was confined to the surface and shallow subsurface, the sunlit realm where plants, microbes, and animals thrived. Yet the borehole, piercing kilometers into rock, thought sterile and inhospitable, revealed subtle traces of a hidden biosphere, challenging our understanding of life's limits and resilience. The discovery of these traces began with microscopic observations of rocks and fluid inclusions. Scientists noted tiny structures resembling microbial filaments embedded in mineral matrices. These were not fossils in the traditional sense, preserved from a surface ecosystem, but signs that microorganisms had once existed and perhaps even persisted at extreme depths. The idea that life could survive in darkness, under crushing pressure, and at elevated temperatures was both humbling and exhilarating. It suggested that life is far more adaptable than we had imagined, capable of exploiting chemical energy sources rather than sunlight, and finding niches in the most unlikely corners of the planet. Further analyses revealed that these microbes likely relied on chemosynthesis, a process akin to what is observed near hydrothermal vents in the deep ocean. Instead of deriving energy from the sun, they harnessed chemical reactions involving minerals and water. Hydrogen, sulfur compounds, and iron within the crust became their sustenance. The deeper layers, previously considered lifeless, emerged as a slow-moving, quiet ecosystem persistent over millions of years. Here, life was not abundant or visible in the conventional sense, but present as a subtle, tenacious thread weaving through rock fractures and fluid-filled channels. Temperature and pressure posed extraordinary challenges to these microorganisms. At depths approaching 12 kilometers, the Kola borehole measured temperatures nearing 180 degrees Celsius and pressures many hundreds of times that of the surface atmosphere. While most known life cannot survive these conditions, certain extremophiles demonstrated remarkable tolerance. Their cellular machinery, particularly enzymes and membrane structures, adapted to operate in high heat and high pressure environments. This adaptation not only broadened our conception of habitability on Earth, but also offered tantalizing hints about the potential for life elsewhere, on planets and moons where conditions are extreme by human standards, yet may be perfectly suitable for resilient microbial ecosystems. The presence of fluids in deep fractures was critical for this subterranean life. Water, even in small quantities, served as a medium for chemical reactions and a conduit for nutrient transport. The interplay of fluids and minerals created microhabitats that could sustain life over geological timescales. This understanding transformed the notion of the deep biosphere from a theoretical possibility into a tangible, measurable reality. The Earth, in its silent, hidden layers, was alive in ways previously unimagined, a planet whose vitality extends far beyond the reach of sunlight. Beyond its biological significance, the deep biosphere has implications for geochemistry and planetary evolution. Microbes influence mineral deposition, alter the chemical composition of rocks, and even participate in the cycling of elements such as carbon and sulfur. In this sense, life at depth is not merely passive. It is an active participant in shaping the planet's interior. Over millions of years, microbial activity may have contributed subtly to the formation of certain minerals, the movement of fluids, and the chemical stratification of the crust. The borehole thus revealed a quiet partnership between life and geology, a collaboration that unfolds slowly, imperceptibly, over immense spans of time. These discoveries also inspire reflections on human resilience and curiosity. The Kola Super Deep borehole required careful design and immense patience, mirroring the tenacity of the microorganisms it revealed. Scientists did not witness the microbes directly in their natural state, nor did they interact with a bustling ecosystem. Instead, they interpreted subtle chemical and structural clues. This approach, careful, indirect, and persistent, echoes the way life itself survives in hidden, extreme environments. Both science and nature rely on adaptability, observation, and the capacity to thrive under constraints. From a philosophical perspective, the deep biosphere challenges our sense of scale and significance. While humans dominate the surface of the planet, life thrives quietly in dimensions far removed from our daily experience. Microbial colonies in deep rock layers may occupy volumes far exceeding the biomass of visible ecosystems. They operate on timescales spanning millions of years, indifferent to seasons, climate, or human activity. This realization cultivates humility, reminding us that the Earth is not merely a backdrop for our lives, but a complex, layered system with countless stories unfolding beyond our perception. Moreover, the deep biosphere opens questions about life in the universe. If microorganisms can survive kilometers beneath the Earth's surface, could similar life exist beneath the crust of Mars, Europa, or Enceladus? Could these alien ecosystems rely on chemosynthesis, insulated from harsh surface conditions by layers of rock or ice? The Kola borehole, in its silent descent, comes not only a record of our planet's history, but also a lens through which we imagine the possibilities of life beyond Earth. It hints at universality, that life, where conditions permit, finds a way to persist, adapt, and endure. In essence, the deep biosphere revealed by the Kola Super Deep borehole is both a scientific and a philosophical marvel. It exemplifies the resilience of life, the hidden complexity of the Earth, and the patient curiosity of humanity. Life exists not only where we can see it, but also in the quiet, pressurized, dark layers of rock. A subtle thread weaving through time and space. By studying these microorganisms, we glimpse the hidden vitality of the planet and gain a renewed sense of wonder at the quiet perseverance of life itself. Section 4. Chemical Mysteries of the Crust. As the Kola Super Deep borehole plunged deeper into the Earth's crust, it unveiled not only geological and biological surprises, but also a realm of chemical mysteries that challenged long-standing assumptions about the planet's composition. Beneath the familiar surface lies a hidden world of intricate mineral structures, unexpected elements, and dynamic chemical processes, quietly shaping the Earth over billions of years. The deeper the scientists drilled, the more they realized that the crust is not a static, uniform shell, but a vibrant, reactive system where chemistry unfolds on scales both microscopic and monumental. One of the most striking discoveries was the abundance of hydrogen in deep rocks. Geologists had not anticipated finding significant amounts of this simple, yet reactive element so far beneath the surface. Hydrogen appeared in pockets of fluid, trapped within fractures, sometimes bound in minerals, and sometimes in nearly pure form. Its presence raised profound questions about how it arrived there, how it interacts with surrounding materials, and whether it might serve as a subtle energy source for microorganisms in the deep biosphere. In this hidden domain, hydrogen became more than a chemical curiosity. It was a lifeline, a potential catalyst for life and chemical reactions in an environment thought barren. The borehole also revealed unexpected distributions of metals and rare elements. While surface rocks had been extensively studied, deep crustal layers contained concentrations of elements like gold, silver, and rare earth metals in forms and quantities that surprised scientists. Some minerals formed under high pressures and temperatures, creating crystalline arrangements not seen at shallower depths. The implications were both practical and profound. Understanding these distributions sheds light on the formation of the continental crust, the migration of elements through geological time, and the subtle interplay of heat, pressure, and chemical reactions that continue to shape the planet's interior. One of the most fascinating chemical puzzles involved the behavior of silica and other silicate minerals. At great depths, silicates, typically considered rigid, stable compounds, exhibited unexpected plasticity. The extreme temperature and pressure altered their crystal structures, allowing them to flow and deform in ways previously thought impossible. This plasticity helps explain how deep rocks can adjust to tectonic stresses, participate in mountain building, and slowly shift over geological timescales. The discovery challenged textbook models of rock behavior, revealing a hidden flexibility within seemingly solid materials. The presence of radioactive isotopes added another layer of complexity. Elements such as uranium, thorium, and potassium-40 were found in higher concentrations than expected, contributing to localized heating deep within the crust. This natural radioactivity influences chemical reactions, rock deformation, and the movement of fluids. It also helped explain the unexpectedly high temperatures recorded at the borehole's deepest points. The Earth's crust is, in essence, a living chemical system where radioactive decay and heat generation quietly sustain processes invisible on the surface, yet crucial for the planet's thermal and chemical balance. Fluid chemistry offered yet more surprises. The Kola borehole revealed salty brines and other concentrated solutions trapped within fractures. These fluids contain dissolved minerals, gases, and trace elements, creating microenvironments where chemical reactions continue slowly over millions of years. In some cases, the composition of these fluids suggested interactions between deep rock layers and ancient seawater, captured during geological epochs long past. It is as if the Earth keeps hidden archives of its chemical history, encoded in pockets of fluid, waiting for patient scientists to uncover and interpret them. One particularly striking finding was the presence of hydrocarbons and organic compounds in unexpected layers. Deep sediments, isolated from sunlight and surface ecosystems, contain traces of chemical structures resembling those of oil and gas deposits. While these compounds were not abundant enough to fuel industry, their presence hinted at complex chemical transformations occurring in extreme conditions. Organic molecules could arise from abiotic processes, driven by heat, pressure, and interaction with minerals, suggesting that lifelike chemistry might occur independently of surface biology. This blurs the line between living and non-living systems and deepens the mystery of how Earth's chemical systems operate far beneath the surface. Another revelation came from unusual isotopic ratios found in deep minerals. The proportion of certain stable isotopes, such as oxygen-18 to oxygen-16, deviated from expected patterns. These anomalies provide clues about the history of water-rock interactions, the formation of ancient continental blocks, and the cycling of elements over billions of years. In essence, isotopes became a kind of chemical time machine, allowing scientists to trace processes invisible to the eye and to understand the subtle choreography of reactions shaping the crust since the dawn of the planet. The chemical findings of the Kola borehole also influenced our understanding of geothermal energy and tectonics. Heat generation from radioactive decay, combined with the movement of fluids and plastic deformation of minerals, creates dynamic chemical and thermal gradients. These processes drive the slow convection of heat and material within the crust, influencing the formation of mountain ranges, the movement of tectonic plates, and even volcanic activity at the surface. The Earth beneath our feet is far from inert. It is a subtle chemical engine, quietly operating across scales of time and space. Perhaps most philosophically profound was the sense of hidden continuity and interconnection revealed by the chemical discoveries. Hydrogen, metals, fluids, and isotopes all interact over vast spans of time, linking the surface to the deep crust, the present to the distant past. The Earth is not merely a collection of rocks and minerals, but a complex chemical tapestry, where reactions unfold slowly, imperceptibly, yet with profound consequences for geology, biology, and climate. Studying these reactions encourages both scientific insight and a deep sense of humility. Beneath our feet, the planet operates with patience, precision, and elegance, far beyond human timescales. In conclusion, the Kola Superdeep borehole unveiled a hidden chemical world, rich with complexity and subtlety. Its discoveries reshaped our understanding of the crust, revealing hydrogen as a deep energy source, unexpected distributions of metals, surprising plasticity of minerals, and the quiet persistence of chemical reactions over millions of years. Fluids, isotopes, and organic compounds all contributed to a story of Earth's interior as dynamic, interconnected, and full of mysteries. Each layer drilled offered a meditation on patience, observation, and the remarkable elegance of natural processes operating quietly beneath our feet. Section 5. The pressure and heat of the deep Earth. As the Kola Superdeep borehole descended deeper into the Earth, one of the most relentless and invisible forces confronting the scientists was the increasing pressure and heat of the deep crust. Unlike the familiar environment at the surface, where temperature and atmospheric pressure are mild and predictable, the deep Earth exists under conditions that are extreme, continuous, and often counterintuitive. These factors not only shaped the challenges of drilling, but also revealed the remarkable physical realities of our planet's interior. Pressure in the deep crust is a quiet but omnipresent force. At 12 kilometers, the Kola borehole encountered pressures hundreds of times greater than those at sea level. Every cubic centimeter of rock is subjected to immense weight from the overlying layers, squeezing minerals, fluids, and fissures into configurations rarely seen on the surface. The mechanical properties of rocks change dramatically under such conditions. They may become more ductile, deform gradually, or fracture in unusual ways. Understanding these responses was crucial for both safe drilling and for interpreting geological history, revealing that the deep crust is not merely solid, inert rock, but a dynamic material shaped by immense, persistent forces. Heat, the other invisible but formidable factor, proved equally compelling. Scientists expected temperatures to rise steadily with depth, according to established geothermal models. Yet the measurements exceeded predictions. At the borehole's deepest points, temperatures reached approximately 180 degrees Celsius, far higher than the anticipated 100 degrees Celsius. This unexpected heat slowed drilling, challenged equipment, and revealed that the Earth's crust is thermally more active than previously assumed. Localized heat arises from several sources: radioactive decay of elements like uranium and thorium, the residual heat of planetary formation, and chemical reactions within rocks and fluids. Each contributes to a delicate and complex thermal system, silently influencing the behavior of the deep crust. The interaction of heat and pressure produces profound geophysical consequences. Minerals that are rigid at surface conditions may flow slowly under extreme heat and pressure, allowing rock layers to bend, warp, or gradually creep over geological timescales. Such plasticity explains how mountains rise, tectonic plates shift, and deep fractures form over millions of years. The borehole allowed scientists to observe these properties indirectly, revealing a world where slow, almost imperceptible changes accumulate into monumental effects. In the deep earth, time and material respond in ways that challenge our surface-bound intuition, emphasizing patience, subtlety, and the scale of natural processes. One fascinating effect observed was the behavior of fluids under pressure and heat. Water, gases, and brines trapped in rock fractures experienced dramatic changes. Boiling points rose, solubility increased, and chemical reactions accelerated. These fluids acted as lubricants in some contexts, allowing rocks to slide past one another along faults and fractures. In other cases, fluid pressures contributed to fracture propagation, subtly reshaping the surrounding rock. The interaction of fluids with minerals at high temperature and pressure not only explained chemical anomalies, but also suggested that the deep earth is a quietly dynamic system, continuously reorganizing itself over millennia. Temperature and pressure also shed light on the limits of life in the deep biosphere. Microorganisms discovered in deep rocks must cope with conditions that, for humans, are extreme. Heat high enough to denature proteins, pressure intense enough to collapse delicate cell structures. Yet the presence of extremophiles demonstrated that life can adapt to these extremes, exploiting chemical gradients and mineral surfaces to survive. Heat and pressure, rather than being purely destructive, become part of a subtle ecosystem in which chemistry, geology, and biology interact. The deep earth, in this sense, is both a challenge and a cradle for resilience. From an engineering perspective, the combination of heat and pressure posed constant challenges to drilling operations. Drill bits wore rapidly, casings expanded under thermal stress, and equipment had to be continuously adapted to maintain structural integrity. Each meter drilled required careful monitoring, patience, and creative problem-solving. In this way, the human effort mirrored the natural forces encountered, slow, persistent, and requiring adaptation to conditions far beyond everyday experience. The project became a meditation on endurance, precision, and the art of working in harmony with extreme natural forces. The interplay of pressure and heat also revealed subtle insights into tectonic and geological processes. High pressure, high temperature conditions influence the formation of metamorphic rocks, the mobility of minerals, and the distribution of stress in the crust. Localized zones of weakness and fracture become pathways for fluid migration, chemical alteration, and even seismic activity. By studying these conditions, scientists gained a deeper understanding of how the Earth's interior evolves, how continents grow and shift, and how heat is transported from the planet's interior to its surface. The deep crust is not merely a static support structure for life above. It is a dynamic, reactive participant in Earth's ongoing evolution. Ultimately, the Kola Superdeep borehole offered a meditative perspective on the nature of the deep Earth. Heat and pressure are omnipresent forces that shape rocks, fluids, chemistry, and life itself, operating silently, steadily, and on scales that dwarf human perception. By confronting these conditions, scientists glimpsed the subtle interplay of physics, chemistry, and biology beneath our feet. The borehole serves as a reminder that the Earth is a patient, persistent system, a planet in which immense forces interact continuously, yet with quiet elegance and precise balance. The study of pressure and heat also cultivates philosophical reflection. Humans live in a thin, temperate layer of the planet, largely insulated from these extreme conditions. Yet just a few kilometers beneath the surface, the world is unrecognizable, a realm of slow flows, intense energy, and quiet resilience. This contrast encourages humility, curiosity, and wonder, highlighting the vastness and complexity of natural processes. The Earth's deep interior is a realm where patience and adaptation are paramount, and where even seemingly inert rock carries the memory of forces acting over billions of years. In conclusion, the heat and pressure of the deep Earth, revealed by the Kola Superdeep borehole, transformed our understanding of the planet's interior. Far from a static mass, the deep crust is dynamic, reactive, and alive in subtle ways. Rocks flow, fluids migrate, chemical reactions proceed, and life endures, all under the relentless influence of these fundamental forces. By studying them, scientists glimpsed the hidden rhythms of the Earth, a quiet, persistent world operating on timescales and dimensions far beyond our everyday experience. Section 6. The borehole and the origins of continental crust. The Kola super-deep borehole, beyond its extraordinary depth, offered scientists a rare and invaluable glimpse into the ancient processes that shaped the Earth's continental crust. For centuries, the formation and evolution of the crust remained a subject of speculation. The rocks visible at the surface are only a thin veneer of a much larger hidden world. By penetrating kilometers into the crust, scientists could study ancient rock sequences in situ, witnessing the layered story of continental evolution, preserved for billions of years beneath our feet. The rocks encountered in the borehole told a story of ancient mountain-building events, known as orogenies, which had occurred hundreds of millions of years ago. These metamorphic layers, intensely deformed and recrystallized, reflected cycles of compression, heating, and fracturing. Each layer recorded a moment in geological history: the collision of ancient continental plates, the rise and erosion of massive mountains, and the gradual stabilization of continental blocks. By studying these layers, scientists gained direct evidence of the immense forces that assembled the continents, revealing that the crust is a product of both violent collisions and slow, persistent geological processes. One of the most revealing discoveries was the composition and structure of deep granitic rocks. Granite, abundant in the continental crust, forms through the slow cooling of molten rock deep beneath the surface. At the Kola borehole, the granitic layers were far more heterogeneous than expected, containing pockets of minerals that suggested complex histories of partial melting, chemical differentiation, and tectonic mixing. These findings demonstrated that continental crust is not the uniform shell, but a mosaic of materials formed under diverse conditions over vast spans of time. Each granitic formation is a snapshot of Earth's chemical and thermal evolution, frozen in rock, yet dynamically connected to the processes that continue beneath. The borehole also provided insights into the mechanisms of crustal thickening and stability. Scientists observed alternating sequences of harder and softer rocks, which reflected cycles of compression, metamorphism, and erosion. Softer rocks, more prone to plastic deformation, acted as buffers, absorbing stress and allowing the crust to adjust to tectonic forces without catastrophic failure. Harder rocks, by contrast, maintained structural integrity and preserved ancient chemical and isotopic records. Together, these alternating layers illustrate how the continental crust balances rigidity with flexibility, a principle crucial for the long-term stability of continents over billions of years. Perhaps one of the most profound insights came from isotopic and chemical analyses. Elements like strontium, neodymium, and lead revealed the ages of different rock layers and the sources of their material. These isotopic fingerprints demonstrated that continental crust is not a static product, but a cumulative record of repeated cycles: volcanic intrusions, sediment deposition, metamorphism, and partial melting. Some of the rocks in the Kola borehole were older than 2 billion years, forming part of the ancient craton known as the Fennoscandian Shield. This deep history provides a rare opportunity to understand the processes that created stable continental cores, the foundation upon which modern landscapes and ecosystems exist. The borehole also highlighted the role of fluids and chemical reactions in crustal evolution. Water and other fluids trapped within deep rock layers can influence mineral formation, facilitate melting, and even contribute to the redistribution of heat. Over millions of years, these slow, subtle processes shape the chemical composition and physical properties of the crust. By observing these fluids in situ, scientists could better understand how continents evolve chemically as well as structurally, emphasizing the interplay between solid rock, liquid pathways, and thermal energy in the deep earth. The discovery of deeply buried organic and mineral compounds added yet another layer of complexity to the story of continental formation. Organic molecules trapped in ancient sediments provided evidence of life's chemical footprint, even at depth, while mineral anomalies revealed processes of differentiation and enrichment previously unknown. These findings suggest that continental crust is not merely a mechanical or chemical structure. It is a living archive of Earth's intertwined geological and biological history. Each layer carries silent testimony to processes that span billions of years, patiently recording the evolution of the planet's surface and interior. From a broader perspective, the borehole helped refine theories about how continents grow and stabilize over time. By comparing the deep crustal layers with surface geology, scientists recognized that the visible crust is only the final expression of a long, layered process of accretion, melting, and deformation. Ancient tectonic collisions, intrusions of molten rock, and slow chemical differentiation combined over eons to produce stable continental blocks capable of supporting oceans, mountains, and ecosystems. The Kola borehole, in essence, allowed humans to witness the hidden scaffolding beneath the Earth's surface, the deep story of continental construction that is otherwise invisible to observation. Philosophically, these discoveries inspire a profound sense of connection with deep time. Standing on the surface, humans perceive time in years, decades, or centuries. But beneath our feet, the rocks tell stories that span billions of years, recording collisions, chemical changes, and the quiet persistence of Earth's interior. The Kola borehole transformed abstract geological concepts into tangible reality. Every meter drilled became a journey backward through time, every mineral a witness to processes that shaped the continents long before humans existed. The deep crust is a silent, patient archive, reminding us that the Earth operates on scales both grand and meticulous. In conclusion, the Kola Superdeep borehole offered humanity an unprecedented view of the origins of continental crust. By drilling through kilometers of rock, scientists uncovered ancient granites, metamorphic layers, fluids, isotopic signatures, and organic traces, all telling the story of continents forming, deforming, and stabilizing over billions of years. These discoveries illustrate that the crust is not a static shell, but a dynamic, chemically and physically complex system, shaped by cycles of energy, pressure, and time. The borehole allowed humans to touch deep history, to meditate on the patience and resilience of the planet, and to glimpse the profound processes that built the foundation of the world we inhabit today. Section 7. Drilling Technology and Engineering Challenges. The Kola Super Deep Borehole is not only a story of Earth's hidden depths, but also a remarkable testament to human ingenuity, patience, and perseverance. Reaching over 12 kilometers into the crust required technology that was unprecedented at the time, combined with innovative thinking, careful planning, and adaptation to conditions that constantly defied expectations. The engineering challenges of drilling at such depths were immense, and overcoming them demanded both creativity and resilience. One of the first and most persistent challenges was heat management. As the drill penetrated deeper, temperatures increased far faster than anticipated, reaching around 180 degrees Celsius at the deepest point. This heat threatened to damage drill bits, distort metal casings, and reduce the effectiveness of drilling fluids. Engineers had to develop sophisticated cooling systems to circulate fluids, dissipate heat, and maintain operational stability. Managing temperature became a delicate balance, requiring constant monitoring, adjustments, and innovation. In essence, the drill team was in a continuous dialogue with the Earth itself, responding patiently to the planet's subtle but relentless forces. Pressure presented another formidable obstacle. At depths of more than 12 kilometers, rock pressure could easily crush equipment or jam drill pipes. The immense weight of overlying rock meant that even minor errors could have catastrophic consequences. Engineers responded with specially designed drill bits, reinforced casings, and carefully calculated drilling rates. The equipment had to withstand stresses far beyond typical industrial applications, creating a scenario in which every mechanical component was pushed to the limits of durability. Success demanded a combination of precision engineering and a calm, methodical approach to problem solving. The drill bits themselves became a focal point of innovation. Traditional bits could not survive the extreme heat and abrasive properties of deep metamorphic rocks for more than a few meters. Engineers developed new materials, coatings, and geometries to extend their lifespan and efficiency. These adaptations were not simply mechanical improvements. They represented an evolving understanding of how rocks behave under extreme pressure and temperature. Each modification was informed by careful observation and incremental learning, a slow, patient process that mirrored the geological timescales being studied. Drilling fluids, or mud, were another critical component. These fluids served multiple purposes. They cooled the drill bit, transported rock cuttings to the surface, lubricated the drill string, and stabilized the borehole walls. At extreme depths, the properties of the fluids had to be precisely controlled, accounting for temperature, pressure, and chemical interactions with rocks and minerals. Even minor miscalculations could lead to equipment failures or borehole collapse. The successful design of drilling fluids for the Kola borehole was therefore both an art and a science, requiring careful experimentation, observation, and continuous adaptation. Another challenge was borehole stability. As the drill penetrated fractured and heterogeneous rock layers, there was a constant risk of collapse or deviation. The team used reinforced casings and adjustable drilling techniques to maintain alignment and structural integrity. They also had to account for fluid pressures within the rock, which could vary unpredictably and influence the behavior of the borehole. Maintaining stability demanded a combination of engineering foresight, real-time monitoring, and the ability to adapt methods quickly in response to unexpected conditions. The borehole became a dialogue with the Earth. Every challenge was met with observation, adjustment, and patience. Temperature, pressure, rock composition, and fluids were not the only obstacles. Time and logistics also played a role. Drilling a kilometer of rock in extreme conditions could take months, and every meter added required careful planning, material supply, and operational coordination. Engineers and scientists worked in shifts, often observing minute changes in drilling performance and geological feedback. Patience was essential. The pace of work was slow, deliberate, and methodical. In this environment, human endurance and careful attention became as important as technology itself. Communication and measurement technologies were also pushed to their limits. Instruments had to record temperature, pressure, chemical composition, and rock structure in real time, often transmitting data from extreme depths. Any failure could compromise the understanding of the deep crust and the safety of the operation. This necessitated a network of precise sensors, monitoring systems, and redundancy measures, all operating under conditions that were at the edge of technological feasibility in the 1970s and 1980s. Each measurement provided a glimpse into the hidden world, but also demanded careful calibration, verification, and interpretation. Beyond the technical challenges, the project demanded a philosophical commitment to patience, observation, and learning from failure. The borehole progressed slowly, meter by meter, often requiring months to overcome unforeseen obstacles. Engineers and scientists were forced to adapt their strategies, experiment with new methods, and accept that progress could be unpredictable. The work mirrored the deep processes of the Earth itself, gradual, persistent, and shaped by forces beyond immediate control. In a way, the Kola Superdeep Borehole became not just a technical achievement, but a meditation on perseverance in the face of challenges too immense to overcome at once. The borehole also inspired innovation that extended beyond the project itself. Techniques developed for deep drilling influenced oil and gas exploration, geothermal research, and mining technology. Cooling systems, drill bit materials, borehole stabilization methods, and fluid management strategies all had broader applications. In this sense, the Kola borehole was a quiet engine of technological progress, demonstrating that extreme challenges can foster ingenuity and solutions applicable in many other domains. In conclusion, the drilling technology and engineering challenges of the Kola Superdeep Borehole exemplify a remarkable human endeavor. Heat, pressure, rock composition, fluid dynamics, and logistical complexity combined to create an environment where patience, observation, and adaptation were paramount. The engineers and scientists faced forces that could not be conquered with brute strength alone, They had to learn, innovate, and respect the subtle power of the earth. In doing so, they created a monument, not just to human skill, but to curiosity, persistence, and the quiet dialogue between humanity and the deep planet. Section 8. Surprising Acoustic and Seismic Discoveries. As the Kola Super Deep borehole probed deeper into the Earth's crust, it revealed a dimension of the planet that is often hidden from human perception. The subtle symphony of sounds and vibrations reverberating through rock layers. While the borehole was primarily a geological project, the drilling process and accompanying instrumentation unveiled acoustic and seismic phenomena that astonished scientists, reshaping our understanding of how the Earth behaves deep beneath the surface. One of the first unexpected observations involved microseismic activity. Instruments installed along the borehole recorded minute vibrations within the rock layers, many of which were invisible to conventional seismographs. These tiny tremors, often only a fraction of the magnitude of an earthquake, revealed that the crust is far from static. Even seemingly solid rock responds subtly to stress, pressure, and the slow accumulation of strain over geological time. The vibrations suggested that the deep crust is a living, responsive system, a place where energy moves quietly, continuously, and imperceptibly, shaping the rock and influencing the surrounding geology. In addition to seismic tremors, researchers noted unusual acoustic signals generated during drilling. As the drill penetrated fractured or mineral-rich layers, it produced sounds that varied in frequency, intensity, and duration. These acoustic signatures provided insights into rock density, fracture networks, and mineral composition. By listening carefully to these subtle signals, scientists could infer properties of the crust without removing every sample. The borehole thus became a kind of subterranean microphone, translating the whispers of the earth into data that could be interpreted, analyzed, and understood. One particularly fascinating phenomenon was the resonance of deep rock layers. Certain sequences of metamorphic and granitic rock vibrated at characteristic frequencies when stressed by drilling. These resonances, detectable only through sensitive instruments, reveal the elastic properties of the crust and how it responds to forces over time. Understanding these resonances is important not only for academic study, but also for practical applications. Predicting how rocks might respond to earthquakes, volcanic activity, or human-induced stress such as mining and drilling operations. The acoustic and seismic data also offered insights into fluid movement at depth. Fluids trapped within fractures and pores subtly alter the transmission of sound waves. Observing how acoustic signals changed as the drill penetrated these fluid-filled zones allowed scientists to map hidden channels of water, brines, and gases. This provided a new perspective on the crust as a dynamic, fluid-influenced system rather than a static assembly of solid rock. Even at extreme depths, the quiet movement of fluids contributes to chemical reactions, heat transfer, and geological evolution, a hidden river running beneath the solid surface. Moreover, the borehole revealed unexpected microfracturing. Tiny fractures, sometimes only micrometers wide, were continuously forming and healing under the immense pressures of the deep crust. Acoustic monitoring showed that these microfractures produced signals analogous to miniature earthquakes, which repeated slowly over time. These observations challenged the perception that deep rock is immovable and inert. Instead, the crust behaves like a slow, living system, continuously responding to stress and adjusting itself over eons. The deep earth, in this sense, is not frozen or silent. It is quietly alive, communicating through vibrations that span scales from microscopic to massive. The study of seismic and acoustic phenomena also illuminated the interactions between heat, pressure, and material properties. Vibrations changed subtly with temperature gradients, indicating that heated rock flows or relaxes differently than cooler rock. Similarly, pressure influenced the amplitude and speed of seismic waves, providing clues about the density and elasticity of deep minerals. By integrating these observations, scientists could build more accurate models of the crust's physical behavior, models that account for not only static composition, but also dynamic processes that operate invisibly beneath the surface. These discoveries have broader implications for earthquake science and planetary studies. Understanding microseismicity and acoustic responses in deep rock informs models of stress accumulation and release in fault zones. It helps predict how energy propagates during seismic events and how deep fluids or chemical reactions may influence rock stability. On a planetary scale, these insights offer a window into the behavior of crusts on other rocky worlds, such as Mars or Venus, where direct observation is limited, but acoustic and seismic monitoring could reveal hidden dynamics. Beyond their scientific significance, the acoustic and seismic discoveries of the Kola borehole have a poetic resonance. The Earth, often perceived as silent and static, is in fact a quiet orchestra of vibrations and resonance. Every fracture, every fluid movement, every subtle stress produces signals that ripple through rock layers, echoing through geological time. By listening carefully, humans are able to connect with the deep earth in a way that transcends mere observation, engaging with the planet as a living, responsive entity, capable of communication through subtle forces that operate on scales beyond immediate perception. The borehole also highlighted the integration of technology, observation, and patience in uncovering these hidden vibrations. Recording and interpreting microseismic signals required precision instruments, sensitive microphones, and careful calibration. Observations had to be made over long periods, often months or years, to distinguish meaningful patterns from background noise. This deliberate, attentive approach mirrors the slow, persistent processes of the Earth itself. Both nature and science operate on timescales that demand patience, careful listening, and an openness to subtle signals that might otherwise be missed. In conclusion, the acoustic and seismic findings of the Kola superdeep borehole revealed a living, vibrating, and responsive deep crust. Microseismic tremors, resonances, fluid-induced signals, and microfractures all illustrate that the Earth is not inert, but quietly active beneath our feet. These discoveries deepen our understanding of the physics of deep rock, the behavior of fluids, and the processes that govern earthquakes and tectonics. More profoundly, they provide a humbling reminder that the planet has a voice, subtle, slow, and persistent, and that by listening, humans can gain a rare insight into the hidden symphony of our world. Section 9. Mineral and Rock Anomalies. The deeper the Kola super-deep borehole reached into the Earth's crust, the more the rocks revealed unexpected and astonishing mineralogical anomalies, challenging assumptions and revealing the intricate complexity of our planet's interior. Each meter drilled was a journey into a hidden world, where rocks, minerals, and chemical interactions told stories billions of years in the making, stories that are invisible at the surface, yet fundamental to understanding the evolution of the Earth. One of the first anomalies that fascinated scientists was the presence of unusually large crystal formations deep within metamorphic layers. While most rocks at the surface contain relatively small, fragmented crystals, the deep granites and gneisses revealed formations several centimeters across. These crystals had formed slowly under high pressure and temperature, often in isolated pockets where conditions remained remarkably stable for millions of years. The size and perfection of these crystals provided a window into the prolonged, patient processes of mineral growth that occur far from sunlight and the disruptive forces of erosion. In addition to crystal size, scientists discovered rare mineral phases that were previously thought to exist only under extreme conditions, such as ultra-high-pressure polymorphs. Some minerals had structures that were theoretically predicted, but rarely observed, revealing the profound effects of depth, heat, and pressure on atomic arrangements. These anomalies challenged geologists to reconsider their models of crustal formation and metamorphism. The deep crust is not merely an extension of surface geology. It is a laboratory of extreme conditions where atoms and minerals arrange themselves in ways that defy conventional expectation. Another unexpected phenomenon was the interlayering of chemically distinct rocks. The borehole revealed sequences where granites alternated with metamorphosed sediments, ultramafic rocks, and other compositions, often in patterns that suggested tectonic folding, intrusion, and partial melting. These complex sequences highlighted the chaotic, dynamic processes that have shaped the continents over billions of years. Deep layers, once considered uniform, turned out to be a mosaic of interactions, each layer a chapter in the Earth's long history of formation, collision, and chemical evolution. Fluids tracked within deep rock fractures contributed to chemical and mineral anomalies as well. Highly saline brines, hydrothermal fluids, and pockets of gas altered the surrounding rock over time, depositing unusual mineral assemblages. Minerals such as sulfides, carbonates, and unusual silicates were sometimes concentrated in microscopic veins or cavities, suggesting that the deep crust experiences localized chemical processes far removed from surface weathering or erosion. These discoveries underscore the idea that the Earth's interior is not inert. It is chemically active, slowly reshaping itself through reactions that occur over millions of years. One of the most intriguing findings involved unexpectedly high concentrations of elements like potassium, sodium, and rare earth metals. These elements, often critical for understanding geological history, were present in pockets and layers far deeper than previously anticipated. Their distribution suggested complex processes of partial melting, fluid migration, and chemical differentiation. By mapping these anomalies, scientists began to understand not only the composition of the deep crust, but also how elements are mobilized, concentrated, and preserved over geological timescales. The Earth's crust emerges as a dynamic repository of chemical diversity, patiently recording the outcomes of processes invisible at the surface. In addition, some layers revealed organic-like carbon compounds trapped in ancient sediments. These compounds were not evidence of recent life, but likely products of chemical reactions under extreme heat and pressure. They hint at a rich, slow chemistry occurring in deep rocks, blurring the line between inorganic and organic processes. These discoveries compel us to consider the deep crust not only as a geological archive, but also as a subtle chemical reactor, where lifelike molecules may form, transform, and persist quietly over millennia. The borehole also revealed anomalies in rock density and elasticity. Certain sequences of rock were unexpectedly soft or pliable, while adjacent layers were exceptionally rigid. These variations influence how stress and seismic waves propagate through the crust, shedding light on earthquake mechanics, tectonic stability, and the flow of heat and fluids. By observing these variations in situ, scientists gained insights into the interplay of structure, composition, and mechanical properties, the deep architecture of the Earth in 3 dimensions. Philosophically, these mineral and rock anomalies inspire wonder at the subtle complexity of nature. From the perfectly grown crystals to the unexpected chemical pockets, the deep crust demonstrates that Earth's interior is neither uniform nor static. It is an archive of slow, patient processes, a theater of chemical interactions and structural evolutions that span millions or even billions of years. Each anomaly is a whisper from deep time, revealing the quiet creativity of the planet beneath our feet. The anomalies also highlight the importance of humility and curiosity in science. Before the borehole, geologists could only speculate about deep crustal compositions and processes. Direct observation revealed surprises that challenged decades of assumption and textbook knowledge. This experience serves as a reminder that nature often holds more complexity than anticipated, and that careful observation, persistence, and open-mindedness are essential for understanding it. Finally, these mineralogical anomalies have practical implications. Knowledge of element distribution, crystal structures, and rock behavior at depth informs mining, geothermal energy exploration, and even planetary science. By studying the Earth's deep crust, humans gain insights that extend far beyond academic curiosity, influencing how we responsibly utilize and interact with natural resources. In conclusion, the Kola Super Deep borehole uncovered a deep world of mineral and rock anomalies that transformed our understanding of the Earth's crust. From rare crystal formations and unusual mineral phases to chemical diversity and structural variability, the borehole revealed the complexity, dynamism, and elegance of the planet's interior. These discoveries remind us that beneath our feet lies a patient, persistent, and intricate world, a slow symphony of chemistry, physics, and structure, unfolding over geological time, waiting for human curiosity to uncover its secrets. Section 10. Fluids, Brines, and Hidden Water. Among the most remarkable revelations of the Kola superdeep borehole was the discovery of fluids and brines trapped deep within the Earth's crust. These hidden reservoirs, often isolated for millions or even billions of years, provide a quiet, unseen dimension of the planet, a world where water, dissolved minerals, and gases interact slowly but persistently, shaping rocks, facilitating chemical reactions, and potentially even sustaining life far beneath the surface. The presence of these fluids challenges the conventional notion that the deep crust is a dry, solid expanse. Instead, deep rock layers contain tiny networks of fluid-filled pores and fractures, where water and brines move with extreme slowness under immense pressure. These micro-reservoirs are not static. They are dynamic systems in which minerals dissolve, precipitate, and migrate over geological time. By studying these fluids, scientists can understand processes that are otherwise invisible, tracing the slow evolution of the crust, the migration of elements, and the interaction between chemical, thermal, and mechanical forces. The composition of these deep fluids is particularly fascinating. Many contain high concentrations of salts, metals, and other dissolved elements, forming brines far more concentrated than seawater. The chemical makeup suggests a long history of interaction between water and rock, where heat, pressure, and mineral surfaces drive slow, persistent reactions. These brines also act as chemical archives, preserving traces of Earth's ancient environments and offering clues about the evolution of the crust over hundreds of millions of years. Fluids in the deep crust play a surprisingly active role in geological processes. For instance, they can lubricate fractures, allowing rocks to move and deform under pressure without fracturing catastrophically. This subtle, almost invisible activity helps explain the slow plasticity observed in some deep rock layers. Fluids also transport heat and chemical energy, slowly altering the surrounding rocks and contributing to metamorphic processes. In essence, they are both actors and witnesses in the ongoing drama of crustal evolution, quietly shaping the Earth over incomprehensible timescales. One of the most intriguing aspects of these deep fluids is their potential role in sustaining microbial life. Extremophiles discovered in deep rocks demonstrate that life can survive far beyond surface conditions, often utilizing hydrogen, methane, or chemical gradients for energy. The presence of brines and trapped water provides an essential medium for such life, creating microenvironments where metabolism and chemical exchange can occur. These findings expand the definition of habitable zones, suggesting that life may persist in places previously thought inhospitable, deep within Earth, or even on other planets. The borehole also revealed unexpected pressure and temperature effects on fluid behavior. Water in fractures remains liquid far beyond its normal boiling point because of the immense pressure, while dissolved gases behave in unusual ways, forming tiny pockets that slowly move through the rock matrix. These behaviors influence mineral precipitation, chemical reactions, and the mechanical properties of the surrounding crust. The deep earth, in this sense, becomes a laboratory of slow, high-pressure chemistry, where time stretches and reactions occur over scales beyond human observation. Another revelation came from the discovery of ancient, isolated water pockets. Some fluids appeared to have been trapped since the Precambrian, carrying chemical signatures of the Earth's early crust and atmosphere. These isolated reservoirs act as natural time capsules, preserving information about conditions billions of years ago. By analyzing isotopic ratios and dissolved compounds, scientists can reconstruct aspects of Earth's chemical history, understanding how water, minerals, and gases evolved alongside the growing continents. The movement of deep fluids also influences heat transfer. As water and brine circulate through fractures, they transport thermal energy from hotter to cooler regions, subtly shaping the geothermal gradient of the crust. This has implications for understanding volcanic activity, tectonics, and even geothermal energy potential. The deep Earth's thermal and chemical systems are therefore intertwined, with fluids acting as mediators, quietly orchestrating energy and material flow beneath our feet. From a broader perspective, the discovery of deep fluids invites reflection on the hidden complexity of the Earth. The planet is often imagined as a solid, static mass beneath the surface. Yet in reality, it is a dynamic, fluid-influenced system. Tiny pockets of water, slowly reacting with rock and carrying dissolved elements, demonstrate that even the deepest parts of the crust are alive with subtle motion and chemical activity. Each milliliter of trapped fluid is a miniature ecosystem and a repository of geological history, a reminder that Earth's processes operate on timescales and dimensions far beyond human perception. Philosophically, these findings inspire a sense of humility and wonder. Water, so familiar and essential on the surface, assumes a different role deep within the planet. Patient, silent, and persistent, reshaping the Earth without spectacle or hurry. Studying these hidden reservoirs encourages a deeper appreciation for the interconnectedness of Earth's systems. Solid rock, fluids, heat, and even microbial life are not separate, but components of a subtle, elegant, and enduring network operating beneath us. In conclusion, the Kola Superdeep Borehole revealed a hidden world of fluids, brines, and trapped water, transforming our understanding of the deep Earth. These reservoirs serve as chemical archives, conduits for heat and material, and potential habitats for life, quietly shaping the crust over geological time. They demonstrate that even the solid-seeming depths of our planet are dynamic, interactive, and full of secrets. In listening to the quiet presence of deep fluids, humanity gains insight not only into geological processes, but also into the profound patience, resilience, and interconnectedness of our planet. Section 11. The unexpected deep biosphere beneath the seemingly solid, impenetrable layers of the Earth's crust lies a hidden world teeming with life. far removed from sunlight, air, and the familiar ecosystems of the surface. The Kola Super Deep Borehole revealed tantalizing hints of this deep biosphere, a realm where microorganisms persist in extreme conditions of heat, pressure, and chemical isolation. This discovery challenged long-held assumptions about the limits of life, transforming our understanding of what it means to survive and adapt on Earth. The microorganisms found in deep rock formations are known as extremophiles, capable of enduring conditions that would destroy most surface life. Temperatures in the borehole's deepest layers approached 180 degrees Celsius, far beyond the boiling point of water at the surface, and pressures were hundreds of times greater than atmospheric pressure. Despite these extremes, bacteria and other microbes inhabit tiny fractures and pore spaces within rocks, metabolizing minerals, hydrogen, methane, and other chemical substrates. Their presence demonstrates that life is not restricted to sunlit, oxygen-rich environments, but can persist in the quiet, patient darkness of the deep crust. One of the most striking aspects of the deep biosphere is its adaptation to extreme isolation. Some microorganisms appear to have been trapped for millions of years in fluid pockets or mineral veins, cut off from surface inputs. Yet even in these extreme conditions, life continues, slow, subtle, and resilient. These organisms often metabolize energy from chemical reactions with minerals, in a process known as chemosynthesis, converting inorganic substances into biological energy. This process mirrors the survival strategies of deep-sea vent communities and suggests that life has a remarkable capacity to exploit the tiniest gradients of energy in otherwise hostile environments. The discovery of life so far beneath the surface also raises profound questions about Earth's evolutionary history. These microbes may represent lineages that have persisted in isolation for immense periods, effectively living fossils that provide insight into the planet's biological past. Studying their DNA and metabolism helps scientists understand not only the evolution of extremophiles, but also the resilience of life itself, offering clues to how organisms endure over geologic timescales. In this sense, the deep biosphere is both a living laboratory and a window into the distant past. Fluids discovered in the borehole, brines, and trapped water pockets play a crucial role in supporting this deep biosphere. These reservoirs provide the chemical medium for microbial metabolism, supplying dissolved minerals, gases, and ions that organisms use for energy. The interplay between fluids, minerals, and microbial life illustrates the interconnectedness of Earth's physical and biological systems. Chemistry and geology do not merely form a backdrop for life. They actively participate in sustaining it. Even in isolation from the surface, the deep crust maintains a delicate balance that supports life in subtle, patient ways. These microbes also demonstrate remarkable metabolic flexibility. In the absence of sunlight, photosynthesis is impossible, yet chemosynthesis and other biochemical pathways enable life to extract energy from the Earth's own minerals. Some organisms produce biofilms, Others form colonies in tiny fractures, and many exist in extremely low concentrations, slowly metabolizing and reproducing over centuries. The deep biosphere is therefore a testament to the persistence and ingenuity of life, thriving in a world where time is measured in millennia and energy is scarce. The existence of the deep biosphere has broader implications beyond Earth. If life can persist in the extreme conditions of the deep crust, isolated from sunlight and surface inputs, it is conceivable that similar life forms could exist on other planetary bodies. Mars, icy moons like Europa or Enceladus, and other rocky planets may host life in subsurface environments, sustained by chemical energy rather than sunlight. The Kola borehole's discoveries therefore not only illuminate our own planet, but also expand our imagination about the universality of life in the cosmos. The deep biosphere also invites philosophical reflection. Life exists where we might least expect it, quietly persisting in conditions hostile to human survival. This hidden persistence challenges the anthropocentric view that life requires temperate, surface-friendly conditions. Instead, the deep biosphere reminds us that life is patient, adaptable, and capable of exploiting even the smallest niches of energy and space. It is a lesson in resilience, humility, and the quiet power of nature to endure beyond immediate perception. From a scientific perspective, studying these organisms presents unique challenges and opportunities. Samples collected from deep fractures must be carefully preserved to avoid contamination, and analyses require sensitive techniques capable of detecting life in extremely low concentrations. Despite these difficulties, the potential insights are profound. Understanding deep microbial ecosystems can inform biotechnology, biogeochemistry, and even the search for extraterrestrial life. These microorganisms are not only survivors, they are guides, revealing strategies that sustain life where humans cannot venture. In conclusion, the Kola Superdeep Borehole revealed an unexpected deep biosphere, a realm where microorganisms endure extreme heat, pressure, isolation, and chemical scarcity. These extremophiles demonstrate life's remarkable adaptability, metabolic ingenuity, and resilience over geological time. Supported by fluids, minerals, and subtle chemical energy, they inhabit a hidden ecosystem that expands our understanding of biology, geology, and planetary possibilities. In listening to the quiet persistence of this deep biosphere, humanity gains a profound sense of connection to the patient, enduring, and interconnected systems that define the Earth, a hidden life quietly thriving beneath our feet. Section 12. The surprising gases of the deep crust. Beneath the solid, seemingly unyielding rocks of the Earth lies a hidden world, not only of fluids and minerals, but also of gases quietly trapped in fractures, pores, and mineral matrices. The Kola Superdeep Borehole revealed the presence of these deep gases, offering insights into chemical reactions, heat flow, and even the possibilities of life in the profound darkness of the crust. This discovery challenged assumptions about the deep Earth, transforming the notion of the crust from a solid, inert shell into a dynamic chemical environment, rich with subtle processes. The composition of gases found in the borehole was unexpected. Scientists detected hydrogen, methane, carbon dioxide, and trace amounts of other volatile compounds, all residing in isolated pockets. These gases are not simply remnants of surface activity. They are generated by chemical reactions within the crust, including the slow decomposition of minerals, the interaction of fluids with rock, and radiogenic processes. Over millions of years, these gases accumulate and concentrate in pockets that act as natural laboratories, preserving a chemical history of deep earth reactions. Hydrogen was particularly fascinating because of its dual role as both a chemical agent and a potential energy source. Deeply trapped hydrogen may react with minerals, facilitating reduction-oxidation reactions that slowly alter the surrounding rock. At the same time, hydrogen provides a potential energy source for microorganisms in the deep biosphere, sustaining life far from sunlight or oxygen. The interplay between trapped gases, rocks, and microorganisms illustrates the interconnectedness of geological and biological processes, where chemical energy quietly circulates through the hidden subsurface. Methane also played a surprising role in deep chemical dynamics. Traditionally associated with biological processes or surface hydrocarbons, methane at depth can arise from abiotic chemical reactions, such as the breakdown of water interacting with ultramafic minerals under heat and pressure. These gases migrate slowly through fractures, occasionally forming microbubbles or dissolving in trapped fluids. By studying methane distribution, scientists gained insight into deep carbon cycling, an essential process that influences Earth's long-term climate regulation and tectonic behavior. The deep crust thus becomes a subtle carbon reactor, quietly managing one of the planet's most important chemical elements. Carbon dioxide, while less abundant, revealed additional mysteries. Its presence in deep fractures indicates that volatiles can move, accumulate, and react under extreme pressure. CO2 may combine with water to form carbonic acid, slowly dissolving minerals and creating new chemical pathways. These reactions occur over millennia, demonstrating the patience and persistence of chemical processes deep beneath the surface. Even gases that seem inert in our everyday experience play essential roles in shaping the mineral and chemical architecture of the Earth's interior. Trace gases, such as nitrogen and noble gases, provided chronological insights. Isotopic analysis allowed scientists to estimate the age and origin of gases trapped in isolated pockets, some of which appear to have been sealed for hundreds of millions of years. These gaseous reservoirs serve as time capsules, preserving the chemical fingerprint of ancient geological events, including crust formation, tectonic activity, and fluid interactions. By examining these traces, researchers can reconstruct aspects of Earth's history that are invisible from surface observations. The physical behavior of these gases was equally intriguing. Trapped under immense pressure, gases behave very differently from their familiar surface states. Hydrogen remains highly compressible. Methane forms dense, supercritical fluids, and CO2 can exist in liquid-like states at high pressure. These unusual states influence how gases interact with rocks, fluids, and microbes. For example, gas pressure may help open or stabilize fractures, facilitating the slow migration of fluids and minerals. In this way, gases are not passive, but actively participate in the evolution and dynamics of the deep crust. From a biological perspective, these gases are a potential lifeline for deep microorganisms. Hydrogen, methane, and carbon dioxide provide chemical energy that microbes can exploit through chemosynthesis. Even in isolated pockets with no sunlight or surface nutrients, life can persist by harnessing these gases, demonstrating the resilience and adaptability of the deep biosphere. In essence, the Earth's interior is not merely a rock archive, but a subtle ecosystem where gases, fluids, minerals, and life interact in slow, patient harmony. The discovery of deep gases also holds implications for planetary science and energy research. Understanding how gases form, migrate, and interact under extreme pressure provides models for exploring other planetary bodies, such as Mars or icy moons, where subsurface gases may similarly sustain chemical or even biological processes. On Earth, studying these reservoirs informs geothermal exploration, deep mining, and understanding natural hazards such as gas-related seismicity. The Kola borehole, in this sense, not only revealed hidden Earth processes, but also guided human knowledge for practical and exploratory applications. Philosophically, the presence of deep gases evokes a sense of humility and awe. While the surface world is governed by sunlight, weather, and immediate perception, beneath the crust exists a world of patient chemical interactions where gases migrate, react, and shape the rocks over millions of years. This slow, silent activity emphasizes the vast scales of time and depth at which Earth operates. It reminds us that the planet is alive in subtle ways, quietly orchestrating the movements of matter and energy far from human view. In conclusion, the Kola superdeep borehole revealed a hidden realm of surprising gases, including hydrogen, methane, carbon dioxide, and noble gases trapped deep within the crust. These gases influence chemical reactions, interact with fluids and minerals, support the deep biosphere, and preserve the chemical history of the planet. Their presence transforms our understanding of the Earth's interior from a static, inert structure into a dynamic, chemically active system. In listening to the quiet movements and reactions of these gases, humanity gains insight into the profound patience, complexity, and resilience of the planet beneath our feet. A subtle world of chemistry, life, and energy that has persisted for eons, quietly shaping the Earth we inhabit today. Section 13. Heat flow and temperature surprises. As the Kola super-deep borehole pierced ever deeper into the Earth's crust, scientists anticipated a steady, predictable increase in temperature, a linear gradient that could be modeled with existing geological knowledge. What they discovered, however, was both unexpected and illuminating, reshaping our understanding of heat flow within the planet. The deep earth does not always adhere to simple expectations. Instead, it is a realm of surprises, gradients, and subtle variations that reflect complex geological processes occurring over billions of years. Early predictions suggested a temperature of around 100 degrees Celsius at depths of 10 kilometers, based on extrapolations from shallower measurements. Yet the borehole revealed a more rapid increase in temperature, reaching approximately 180 degrees Celsius at its deepest point of 12 kilometers. This divergence from expectation forced scientists to reconsider assumptions about the thermal conductivity of deep rocks. Instead of a uniform gradient, heat flow proved to be influenced by variations in rock composition, fluid presence, and microfractures, creating pockets of higher or lower temperature that were invisible to previous surface-based models. One surprising factor was the role of fluids and brines in redistributing heat. Water trapped in deep fractures can transfer thermal energy slowly, while high-pressure brines act as conductors and buffers, redistributing heat in subtle ways. This discovery emphasized that the deep crust is not a static, insulated layer. It is a dynamic system in which fluids act as conduits for both heat and chemical energy. The interplay of thermal gradients, fluids, and rock composition creates an intricate mosaic of temperatures that cannot be captured by simple models alone. Metamorphic and granitic rock layers also contributed to the unexpected thermal behavior. Denser, mineral-rich formations conducted heat differently than surrounding rocks, creating zones of accelerated or decelerated warming. This heterogeneity challenged conventional wisdom and highlighted the importance of in situ measurements. The Earth, it seemed, was more complex than surface models suggested, a reminder that direct exploration is often necessary to uncover the subtle truths of natural systems. Heat flow at depth also influenced mechanical behavior. As temperatures increased, certain rocks exhibited plasticity, slowly deforming under stress rather than fracturing abruptly. This thermal softening affects seismicity, the propagation of stress, and even the migration of fluids. The deep earth is therefore not only chemically active, but also mechanically responsive, shaped by the silent, patient influence of heat over millions of years. Understanding these interactions is crucial for both geology and geophysics, providing insight into earthquakes, volcanic activity, and the slow evolution of continents. Another surprise came from the thermal effects on drilling equipment. Temperatures were far higher than anticipated, complicating operations and threatening the integrity of drill bits and casings. Engineers had to innovate cooling systems, select heat-resistant materials, and carefully monitor equipment performance. In this way, the discovery of unexpected heat not only influenced scientific understanding, but also became a driver of human ingenuity and adaptation. Technology and nature engaged in a patient dialogue, each influencing the other over the course of the project. The variation in heat flow also revealed the ancient geological history of the region. Localized high-temperature zones often corresponded to igneous intrusions or metamorphic events, preserving evidence of tectonic activity from hundreds of millions of years ago. Temperature, in this sense, is not just a physical measurement, but a historical record, encoding the deep Earth's past into gradients that scientists can interpret and analyze. Each fluctuation in heat flow tells a story of continental collision, magma movement, and the slow reshaping of the planet over geological timescales. Beyond scientific implications, these heat flow discoveries invite a philosophical reflection. The Earth's deep interior is patient, enduring, and slow-moving, yet it exerts profound influence over surface life, tectonics, and climate. Heat percolates silently through the crust, driving chemical reactions, supporting hidden life, and shaping rock mechanics. It reminds us that natural processes operate on scales far beyond human perception, patiently, persistently, and with subtle power that shapes our world in ways we rarely notice. The Kola superdeep borehole, often described as a monument to human curiosity, revealed a deep Earth both stranger and more beautiful than imagined. From unexpected heat gradients to hidden fluids, rare minerals, invisible gases, and even life thriving far below the surface, the borehole demonstrated the planet's patient complexity. Each discovery transformed assumptions, challenged models, and deepened our appreciation for the slow, intricate processes shaping the world beneath our feet. The Earth, silent and steadfast, is a teacher of patience, ingenuity, and awe, revealing that even the most hidden corners of our planet hold stories waiting to be uncovered.